A single teaspoon of neutron star material weighs as much as an entire mountain. This is not a fantasy, but the reality within the collapsed heart of a giant star, a place where physics is pushed to its absolute breaking point. By the end of our journey, you will understand the true nature of the most extreme matter in the cosmos and how it holds the key to fundamental secrets of our universe. We will venture into layers where atoms are pressed into entirely new forms and explore the possibility of a core made of pure quark soup. What does it feel like to discover that the universe can create something so impossibly dense? The stellar forge ignites in a final, brilliant flash of light. A star, once a shining beacon, has used the last of its nuclear fuel. For millions of years, a delicate balance held its vast structure in place, with the outward push of fusion energy holding steady against the inward pull of gravity. Now, with that energy fading, the balance shifts in an instant. Gravity takes over. The star's core, a sphere of iron about the size of our world, can no longer hold its form. It yields completely, folding inward in less than a heartbeat. Imagine a structure 1,000,000 stories tall falling into its own foundation, all the space within it vanishing in a single, transformative moment. This incredible inward collapse sparks a powerful rebound, a shock wave of such intensity that it sends the star's outer layers streaming into the void in a supernova explosion that can outshine an entire galaxy. Yet within that expanding cloud of cosmic material, something new and wondrous remains. The surviving core, having endured the immense transformation, is now an object the size of a city holding more mass than our sun. It is a neutron star, and the substance within it has been changed into something truly extraordinary by the profound events of its origin. This solid iron crust is the last familiar ground in an alien landscape. Picture it as a perfect, unbreakable crystal shell, forged in the final moments of the star's transition. But the forces increase dramatically as we journey inward, reshaping reality itself. Just beneath this outer layer lies the inner crust, a place where the rules of chemistry are rewritten. Here, atomic nuclei are pressed so tightly they are forced into contact, no longer floating in empty space but drawn together like a crowd in a cosmic subway car. This immense pressure creates unusual new shapes scientists call nuclear pasta, a name that hints at its strange forms. Some nuclei flatten into sheets like lasagna, while others are stretched into long, thin strands resembling spaghetti. This is matter on the verge of changing its nature, a transitional state between the world of atoms and something entirely new. The true mystery, however, lies at the very heart of the star. Below the pasta layer, the forces become so overwhelmingly immense that even these exotic structures cannot hold. The protective barriers that define a proton or a neutron give way. Individual atomic identities dissolve completely, and we enter the core. What remains is a vast, dense sea of neutrons, a quantum fluid so perfect it can be described as a single, city-sized atomic nucleus. But is that the final layer, or is there something even more fundamental hidden within? Could the neutrons themselves transform under this unbelievable strain, releasing their constituent parts into a soup of pure quarks, the most basic building blocks of matter? This layered structure is our only map into a realm of physics we cannot visit, a natural laboratory that challenges our deepest understanding of what stuff is and what it can become. This transformation is the final surrender of atomic identity. Within that crushing inner core, the very definition of matter is rewritten. A proton, one of the fundamental building blocks of an atom, cannot exist on its own here. An electron, the tiny, buzzing particle that gives matter its structure, is forced into a union it would never experience otherwise. The star's immense gravity presses these electrons directly into the atomic nuclei, where they meet with protons. In that instant, a kind of alchemy occurs. The proton and electron merge, cancelling each other's charge and transforming into a neutron, while a ghostly particle called a neutrino flees the scene at nearly the speed of light. This process, known as inverse beta decay, is the engine that powers the star's final metamorphosis. The result is a substance unlike any other. The space that normally separates particles in a gas, a liquid, or even a solid is entirely eliminated. What emerges is a single, continuous ocean of neutrons, a quantum fluid of unimaginable density. Picture a crowd so dense that every individual merges into a single, flowing entity. This is the neutron sea, a state of matter that exists nowhere else in the universe under stable conditions. It behaves as one unified superfluid, flowing without any friction whatsoever. But such an extreme state cannot exist without a counterbalance. What mysterious force pushes back against this immense weight, preventing the entire star from collapsing further into an infinitely small point? The answer lies in a strange and powerful quantum rule. This resistance is a quantum rule made manifest, a fundamental law of the universe that says no more. Inside the core, every neutron is identical in type, but the Pauli exclusion principle dictates that no two can share the same energy state or position. They are forced into a kind of cosmic personal space, a fundamental refusal to be compressed into the same identity. As gravity squeezes them ever closer, this rule creates a powerful outward push known as degeneracy pressure. It is not a force born of heat or collision, but of pure quantum identity. Imagine a room filled with an immense crowd where every single person is utterly identical, yet a fundamental law prevents any two from standing in the exact same spot. The more you try to compress the crowd, the more fiercely this rule pushes back. This is the rebellion happening at the heart of a neutron star. It is a silent, persistent pressure that exists even at absolute zero, a final line of defense drawn not by energy, but by the very rules that define what a particle is. This quantum standoff is the only thing preventing the entire stellar mass from continuing its inward journey to become a black hole. Yet this leads to a profound question. What happens when gravity becomes so overwhelmingly powerful that it finally overcomes even this fundamental rule? What is the ultimate fate of matter when its last defense can no longer hold? Yet even this quantum rebellion has its breaking point. Deep within the most massive neutron stars, the pressure can become so overwhelming that the identity of a neutron itself is erased. The very particles that form the star's final defense are forced to surrender their structure. Think of a neutron not as a solid ball, but as a tiny, tightly bound bag containing three even more fundamental particles called quarks, held together by gluons. Under normal circumstances, these quarks are eternally confined, never allowed to wander freely. But at the very heart of a neutron star, the pressure may be so unimaginably immense that it overwhelms the force that binds them. The bag, in a sense, rips open. The neutrons dissolve. What is left is a seething, primordial soup where quarks and gluons mingle freely, a state of matter known as a quark-gluon plasma. This is not a gentle transition. It is the final deconstruction of matter as we know it, a return to the universe's most fundamental ingredients. This quark matter core, if it exists, is a direct window to the first microseconds after the Big Bang, when the entire cosmos was filled with this exact same fiery, fundamental soup. For a fleeting moment after the birth of everything, this was the only state of matter in existence. Then the universe expanded and cooled. and quarks were forever locked away inside protons and neutrons, imprisoned for billions of years. The core of a massive neutron star might be the only place in the modern universe where this ancient, primordial state of matter endures. But how could we ever confirm the existence of something hidden deep within an object thousands of light years away? We cannot visit a neutron star, so we must instead learn to read the subtle messages it sends across the void. These cosmic lighthouses are known as pulsars, and their discovery was a moment of true scientific wonder. A pulsar is a neutron star in rapid rotation, and its immense magnetic field acts like a cosmic particle accelerator. This field funnels intense beams of radiation from the star's magnetic poles, and as the star spins, these beams sweep through space. If one of these beams happens to point in Earth's direction as it rotates, our telescopes detect a flash, a pulse of energy. The rhythm of these pulses is breathtaking in its precision, ticking with a regularity that can surpass the most advanced atomic clocks we can build. This is not a steady light but a strobe, a beacon blinking from thousands of light years away. The entire phenomenon relies on a perfect, and somewhat fortunate, alignment between the star's rotation, its magnetic field, and our line of sight. This precise clockwork allows scientists to use pulsars as tools for incredible experiments. By tracking the subtle changes in the timing of their pulses, researchers can detect the gravitational waves rippling through spacetime, study the tenuous gas between the stars, and even test Einstein's theory of general relativity under extreme conditions. All of this power and precision originates from the star's unimaginably dense interior and its phenomenally strong magnetic field, a force that shapes the very space around it. But the universe always finds a way to push extremes even further. Among these stellar remnants exist true magnetic monsters, a rare class of neutron stars known as magnetars. Their magnetic fields are not just strong, they are almost beyond comprehension, trillions of times more powerful than Earth's own protective magnetic shield, or even the field of a typical neutron star. This force is so immense that it warps the very fabric of reality around the star. It can literally twist the shape of an atom, stretching it from a sphere into a needle-thin thread. The solid crust of the star is not immune to this power. It is under constant, unimaginable strain. Just as tectonic plates on Earth shift and cause earthquakes, this crust can fracture under the magnetic stress, creating starquakes. The energy released in one of these events is staggering. In a mere tenth of a second, a single crack can unleash a flare of gamma rays and X-rays that outshines our entire Milky Way galaxy. For one brilliant, fleeting instant, a single object no bigger than a city can produce more light than every other star in our galaxy combined. This phenomenal magnetism is a relic of the star's dramatic birth. During the supernova collapse, the star's original magnetic field is compressed and wound up by the rapidly spinning core, amplifying it to these incredible levels. These magnetic behemoths are more than just cosmic curiosities. They are natural laboratories that let us test the absolute limits of magnetic field strength. And because energy and mass are two sides of the same coin, this incredible magnetic energy actually contributes to the star's gravity, warping the space around it in ways we are only beginning to understand. How do you observe an object whose most dramatic eruptions are unpredictable and brief? You must be watching at exactly the right moment, or you must learn to read the lasting marks its power leaves on the cosmos. The sheer compactness of a neutron star defies all earthly intuition. We speak of a mass greater than our sun compressed into a sphere no wider than a modest city, but the true meaning of that statement only hits when you consider the numbers. The density here is hundreds of millions of tons for every single cubic centimeter. To hold that in your mind, picture a single sugar cube of this material. That tiny block would weigh as much as every human being on our planet combined. This incredible density creates a gravitational pull billions of times stronger than what we experience on Earth. The force is so overwhelming that if you were to somehow stand on its surface, you would be instantly transformed, your atoms merging seamlessly with the star's crystalline crust. Even light struggles to escape this grip. The velocity required to break free from its surface is a significant fraction of the speed of light itself. This is not the gentle tug of our home world, but a fundamental warping of the rules of escape. So how do we possibly measure the mass of such a distant, impossible object? The universe provides a natural scale in the form of binary systems, where two neutron stars orbit one another in a silent, cosmic dance. By observing the precise timing of their orbits, especially the flashes from a pulsar partner, scientists can calculate their masses with astonishing accuracy. Each precise measurement is a data point that either supports or challenges our theories about the nature of matter itself. These masses are the critical constraints for the equation of state, the fundamental physical rule that describes how matter pushes back against gravity at these unimaginable densities. A slightly heavier measured mass might rule out the possibility of a soft quark matter core, suggesting that neutrons can withstand even greater pressure. A lighter mass might allow for more exotic possibilities deep within. Every new measurement is like placing a weight on a cosmic scale, testing our models of physics under conditions we can never hope to recreate. The true nature of the star's heart is written in the numbers that define its total weight, a silent message about the strength of matter at its absolute limit. This single equation, known as the equation of state, acts as the ultimate guidebook for matter under absolute extremes. It is not a simple formula, but a profound description of how substance behaves when there is no room left to behave. The equation of state defines the precise relationship between the incredible density at the star's heart and the resulting pressure that pushes back. This fundamental rule dictates everything about the star's anatomy, its maximum possible mass, and its final radius. It is the single line of code that runs the entire system. Think of it as the architectural plan for a building where the very bricks are changing their nature. One design might call for a sturdy structure built entirely of neutrons, holding firm against gravity's pull. Another, more exotic blueprint might allow the central pillars to dissolve into a quark gluon core, creating a hybrid star with a soft, fluid heart. Which of these blueprints is correct? The answer is written in the cosmos, and we are learning to read it through incredible observations. The mergers of neutron stars send ripples through the fabric of space-time itself, gravitational waves that are captured by sensitive detectors here on Earth. The specific shape of these ripples encodes vital information about how stiff or soft the star's internal matter is, directly probing its equation of state. Each new signal is another piece of the puzzle, narrowing down the possibilities for what matter can truly become. Unlocking this master equation does more than just satisfy our curiosity about these distant objects. It reveals the fundamental properties of nuclear matter, the same stuff that makes up most of the visible universe. By understanding the heart of a neutron star, we are ultimately understanding the deepest rules that govern reality itself. The silent collision of two neutron stars sends a tremor through the cosmos that we can now feel. In 2017, observatories on Earth detected the subtle shiver of an event designated GW170817, a ripple in spacetime that had journeyed for 130 million years. This was not a flash of light or a burst of radio waves, but a gentle stretching and squeezing of the universe's fabric, a gravitational wave born from the final, spiraling dance of two ancient stellar remnants. The unique wobble and chirp of that signal carried a hidden message, a direct readout of the star's masses and how they influenced each other's forms just before they came together. This tidal deformation is the essential clue. Imagine two spheres of the densest material possible, circling one another in a tightening orbit. Their immense gravity does not just pull, it stretches them, like the moon's pull on Earth's oceans but on an unimaginable scale. How readily they stretch reveals everything about the stiffness of the matter deep within. A signal that suggests soft, easily shaped stars points toward a unique quark matter core. A signal of firm, resistant stars suggests neutrons holding their structure. Each new detection is like placing a key into the lock of the equation of state, testing which theoretical key turns the mechanism. But the story of this cosmic meeting did not end with the gravitational wave. Moments later, space-based telescopes observed a brilliant flash of gamma rays, and for weeks afterward, observatories around the world watched as the aftermath unfolded into a vibrant, hot cloud. The incredible energy of the merger was forging new atoms, creating heavy elements like gold, platinum, and uranium, and scattering them across the void. This means the gold in a wedding ring or the uranium that powers reactors was likely created in an event like this, a powerful union that seeds the galaxy with the ingredients for new worlds and ultimately for life itself. We are not just distant observers of these events, we are made from them. This cosmic forge operates on a principle of incredible speed and abundance. During the brief, energetic merger of two neutron stars, countless free neutrons are released from the stellar material. These neutrons are the raw ingredients for a cosmic alchemy known as the rapid neutron capture process, or the R process for short. In this environment, ordinary atomic nuclei are showered by this dense neutron flow. They do not just absorb one or two, they gather them in an instant, quickly building into unstable, heavyweight forms. This intense gathering cannot last. The enlarged nuclei are fundamentally unstable, and they soon undergo a transformative change, converting some of their neutrons into protons. This shift changes their very identity, creating new, stable elements heavier than iron. It is a breathtakingly fast assembly line, producing in mere seconds elements that would take stars billions of years to form through slower fusion. The gold in a treasured heirloom, the platinum in a catalytic converter, and even the uranium that can power a city were likely born in this dynamic, explosive event. We often say we are made of stardust, and that is true for the common elements of life like carbon and oxygen. But the heavier, rarer atoms that define our technology and adorn our culture, they carry the specific signature of a neutron star collision. These powerful events are not merely endpoints, they are essential crucibles that seed galaxies with the ingredients for new planets and, ultimately, for new possibilities. The dramatic transformation of ancient stars directly enables the rise of complex worlds, weaving a profound connection between the most energetic events in the universe and the delicate emergence of life. This solid surface is a realm of impossible physics. The outer crust of a neutron star is not like any rock we know. It is a perfect, unbreakable crystal forged in the final moments of the star's collapse. Here, iron nuclei are packed into a rigid lattice structure, but they have been stripped of their electrons. There are no atoms left, only the bare, dense nuclei of iron held in a perfect crystalline pattern, all floating within a strange, pressurized sea of electrons. This degenerate electron gas is what gives the crust its incredible strength, creating a solid that is 10 billion times stronger than any steel. It is the hardest material in the known universe. On this surface, topography is measured in centimeters. A slight imperfection, a wrinkle in the crust that we would barely feel underfoot on Earth, constitutes a mountain. But these are mountains with the mass of the entire Himalayan range compressed into a bump the size of a small hill. The gravitational force is so intense that it prevents any larger formations from existing, flattening any potential peak into a subtle, yet unimaginably dense contour. This crust is under constant, unbelievable strain from the forces beneath it and the immense magnetic fields twisting through it. Like the tectonic plates of our own planet, this crystalline shell can fracture. When the stress becomes too great, the crust breaks in a starquake. This sudden shift is so powerful that it can momentarily change the star's rotation, causing the perfectly timed pulses from a pulsar to stutter or glitch. These tiny hiccups in the cosmic clock are our direct evidence of the solid ground shifting under pressure. By studying these glitches, we can listen to the star's surface tremble and, in doing so, learn about the nature of the mysterious fluid layers that lie just beneath this brittle shell. Deep within the inner crust, matter undergoes a transformation that defies all common sense. Here, at densities 1,000,000 times greater than water, atomic nuclei are pressed so tightly together that they lose their individual identities. They no longer float in isolated spheres but are forced into contact, merging into bizarre, interconnected shapes. Scientists, with a touch of poetic license, call this exotic state nuclear pasta. It begins with long, thin rods that resemble spaghetti. As the pressure increases, these rods flatten into wide, continuous sheets like lasagna. The progression does not stop there. Under even greater force, the sheets contort into hollow tubes or complex, honeycomb-like waffles, and finally into isolated bubbles of nuclear material floating in a sea of neutrons. This is not a gentle reshaping. It is matter being forced into a new phase of existence, a state that bridges our familiar world of solids and the alien quantum fluid of the core. The strength of this material is almost beyond calculation. Its tensile strength is theorized to be billions of times greater than the strongest steel, making nuclear pasta the most durable substance in the known universe. This incredible rigidity means the pasta layers do not break easily, but when they do, the results are cosmic. A single fracture in this unimaginably strong lattice could release a tremendous amount of energy, potentially causing the entire star to shift its rotation in a sudden, observable event known as a pulsar glitch. This bizarre transitional matter exists in a fleeting balance, a unique and unstable state that can only form under the specific, crushing conditions found only here. It is a natural laboratory demonstrating the profound and strange ways matter can behave when pushed to its absolute limits. Deep within the star's core, friction is a forgotten concept. The neutron sea, that vast quantum fluid, is expected to transform into something even more extraordinary, a superfluid. This means it flows with absolutely zero viscosity, encountering no resistance whatsoever. At the same time, the small fraction of protons mixed within this sea may form a superconductor carrying electrical current without any loss of energy. These are not small-scale laboratory effects, but quantum behaviors operating on a staggering, stellar scale. The entire interior of the city-sized object becomes a frictionless engine. This incredible lack of resistance helps explain one of the star's most puzzling behaviors, the sudden speed up in a pulsar spin known as a glitch. Picture the star's solid crust spinning at one steady rate, while deep inside, the superfluid core rotates as a sea of tiny, organized whirlpools called vortices. These vortices are normally held in place by the crust's crystalline structure. But as the star gradually slows its spin over millennia, the superfluid can become stuck, spinning faster than the crust. When the strain becomes too great, these vortices suddenly break free all at once, transferring a massive burst of angular momentum upward. It is as if a spinning ice skater suddenly pulled their arms in, causing a rapid, observable jump in rotation. This sudden transfer of energy from the frictionless interior to the solid crust is the hidden mechanism behind the pulsar's timing glitch. The existence of such macroscopic quantum phenomena is a direct result of the extreme density and coldness within, creating an environment where the rules of the very small govern the behavior of the entire star. This frictionless interior also has a profound influence on the star's immense magnetic field, shaping how it evolves over millions of years and potentially powering the dramatic outbursts we observe from light years away. The origin of a neutron star's magnetic personality is a puzzle written in the moments of its dramatic birth. How does a star create a magnetic force trillions of times stronger than anything we can produce on Earth? One compelling idea is the fossil field hypothesis. Picture the original star, a giant with its own widespread magnetic field. When its core collapses, that magnetic field is not destroyed. Instead, it is preserved within the shrinking material. As the star compresses from a sphere larger than our Sun down to a city-sized object, the magnetic field lines are squeezed together incredibly tightly. This compression alone can amplify the original field by a factor of billions, keeping a memory of the star's former life in an intensely concentrated form. Yet there is another powerful mechanism that may be at work in the first turbulent seconds of the star's existence. This is the dynamo theory. In the dynamic aftermath of the supernova, the newborn neutron star is a seething, rapidly rotating ball of hot, conductive fluid. Enormous convection currents, like boiling water in a pot but on a cosmic scale, churn this material. In any rotating, conductive fluid, this motion can generate a self-sustaining magnetic field, much like the dynamo inside Earth that creates our planet's magnetic shield, but operating with tremendous intensity. The rapid spin and incredible heat provide the perfect engine to build a weak seed field into a global magnetic phenomenon. The true story is probably not one or the other, but a complex interplay of both processes. A pre-existing fossil field could provide the seed that a powerful dynamo then amplifies to even greater extremes. The specific path taken, the initial spin, the progenitor star's mass, all these factors might determine whether a neutron star becomes a steady pulsar or a volatile magnetar. This magnetic fingerprint, imprinted at birth, guides the star's entire future. It governs how the star spins down over millennia, how it emits its beams of radiation, and how its interior, superfluid core cools. The magnetic field acts as a conduit, channeling the star's internal thermal energy outward into space. A stronger field can lead to more rapid cooling, while a weaker one might allow the star to retain its heat for longer. The star's magnetic character is therefore not a static trait, but a dynamic force that shapes its life from its first second to its final, quiet state. Even the hottest stellar embers eventually surrender their warmth to the cold of space. A newborn neutron star enters the universe at a blistering temperature of over 1 billion degrees, but this incredible heat does not last. The star's journey toward coldness is not a simple process of radiating warmth from its surface. It is a far more dramatic and revealing transformation, driven by ghostly particles escaping from its very heart. The primary engine of this cooling is the neutrino, an almost massless particle that interacts so weakly with matter it can pass through light years of lead without a single collision. Deep within the star's core, exotic nuclear reactions and particle collisions generate these neutrinos in staggering numbers. They stream outward, carrying the star's thermal energy away into the void at nearly the speed of light. This neutrino emission is so efficient that within a mere million years, the star's internal temperature plummets by a factor of 1,000. But the exact path of this cooling, the star's personal cooling curve, holds a secret message about what is happening deep inside. This invisible cooling process creates a unique observational fingerprint. By carefully measuring the surface temperatures of neutron stars across a range of ages, from the youthful to the ancient, astronomers can plot a cooling curve. This graph acts as a cosmic thermometer probing directly into the star's inaccessible core. A star that cools more rapidly than standard models predict is sending a clear signal. Its internal engine is running hotter and more efficiently than a simple sea of neutrons would allow. This accelerated cooling points directly to the presence of exotic matter. If the core contains a soup of free quarks, or if other exotic particles like pions or kaons are being created, they provide powerful new pathways for neutrino production. These additional channels act like opening extra vents in a furnace, allowing the star's internal heat to drain away at a much faster rate. A rapidly cooling neutron star is therefore not just growing cold. It is actively broadcasting the composition of its deepest interior. The final state of an old neutron star is a profound quiet. After its first million years of rapid neutrino cooling, the star transitions to a slower, more conventional cooling phase where it simply radiates photons from its surface. Its internal dynamo has quieted, its rapid spin has slowed, and its dramatic flares have ceased. It becomes a cold, dark crystal drifting through the void, a diamond forged in a supernova's fire. Yet even in this silent state, it remains an object of immense density and mystery, a relic holding within its frozen structure the encoded history of the most extreme matter in existence. Every line on this graph tells a different story about the heart of a star. The relationship between a neutron star's mass and its radius is our most fundamental diagnostic tool, a cosmic fingerprint that reveals the true nature of the matter within. This is the mass-radius relation, and it acts as a direct translator for the equation of state. Think of it this way. If the matter inside is soft and easily compressed like a pillow, then adding more weight, more mass, will cause it to shrink significantly. A softer equation of state predicts that more massive neutron stars will have smaller radii. But if the internal matter is stiff and resists compression, like a solid rubber ball, then even piling on immense mass will not make it much smaller. A stiffer equation of state predicts that stars will maintain larger radii across a wide range of masses. The precise numbers on this plot are the ultimate guide, pointing toward what truly lies at the core. So how do we measure the size of an object thousands of light years away? One method uses powerful X-ray telescopes. When a neutron star gathers material from a companion star, its surface heats up and glows with thermal emission. By carefully analyzing the spectrum and intensity of this X-ray light, scientists can model the star's surface and infer its radius. Another, more dynamic method comes from the gravitational waves of mergers. As two neutron stars spiral together, their immense gravity stretches them, creating tidal bulges. The degree of this deformation, encoded in the gravitational wave signal, is exquisitely sensitive to the star's internal stiffness, which is directly tied to their radius. Each new data point, whether from a flickering X-ray source or a ripple in space-time, places a dot on this grand cosmic graph. Where those points fall will answer the most profound questions. Do they cluster in a way that suggests a core of pure neutrons, or do they point toward the existence of a strange, soft heart of free-flowing quarks? The mass-radius relation is the universe's own way of charting the final frontier of matter itself. There is a final line beyond which a neutron star cannot exist. This ultimate threshold is defined by the maximum mass it can sustain before its internal structure can no longer hold. The quantum pressure from its densely packed neutrons, the very force that supports it, can only resist gravity up to a certain point. Add just a little more material and this delicate balance is lost. The entire star, every mountain of matter compressed into a sphere the size of a city, would disappear from our universe, leaving behind only the profound quiet of a black hole. This maximum mass is not a random number. It is the most critical prediction of the equation of state, the fundamental rule describing matter's final stand. Current observations of binary systems point toward a limit somewhere between 2 and 2.5 times the mass of our Sun. Finding a neutron star with a mass hovering near this theoretical ceiling would be a revolutionary discovery. It would act as a strict filter for our theories, immediately ruling out models of matter that are too soft or exotic to support such immense weight. A star this massive could not possess a large, soft core of quark matter, for instance, as such a structure would give way under the strain. Its very existence would be proof of an incredibly stiff and resilient interior, one where neutrons or other particles hold their form against nearly impossible odds. This mass limit represents the ultimate confrontation between the large-scale force of gravity and the small-scale rules of quantum identity. It is a frontier we are mapping not with physical probes, but with precise measurements of distant, spinning beacons. Each new mass determination brings us closer to answering the final question: how much can you weigh before you are no longer a thing, but a place where space-time itself is profoundly changed? The universe's imagination for creating strange objects far outstrips our own. Beyond the established territory of neutron stars lies a theoretical frontier populated by entities that challenge the very definition of a star. One such candidate is the strange star, a concept that dares to ask a radical question. What if the transformation did not stop at the neutron sea? What if the pressure was so immense that it converted not just the core, but the entire star into a single, massive droplet of quark matter? This would be a strange star, an object composed almost entirely of up, down, and strange quarks, a flavor that is normally fleeting and rare. The idea hinges on a profound possibility that this strange quark matter could be the most stable form of matter in the entire universe, more stable than even iron. In this scenario, a neutron star would not be an endpoint, but merely a way station on the path to becoming this ultimate, fundamental object. The transition would be total, leaving behind a stellar remnant with no solid crust, a perfect, self-bound sphere of pure quark soup. An even more ethereal concept is the boson star. While neutron and strange stars are made of fermions, the particles that constitute matter, a boson star would be built from force carriers. Picture a star not made of quarks or electrons, but of particles like gluons or even the hypothetical actions, gathered into a giant, coherent quantum state. It would be a star made not of stuff, but of pure interaction, a ghostly orb of condensed energy holding itself together through its own quantum rules. These objects have never been confirmed, and they may not exist at all. Yet the very act of searching for them, of contemplating their possibility, forces our physics to evolve. The hunt for these phantoms in the dark compels us to ask not just what is, but what could possibly be, redefining the ultimate limits of material form in the cosmos. Our understanding of these distant giants is assembled not from a single photograph, but from a symphony of data. Since we cannot travel to a neutron star, we have become masters of indirect observation, interpreting the faint whispers and loud tremors they send across the cosmos. The steady, metronomic pulse of a rotating pulsar acts as our most reliable clock. By tracking the minuscule variations in this rhythm, astronomers can detect the presence of orbiting planets, measure the star's tiny wobbles, and even sense the subtle stretching of spacetime caused by passing gravitational waves. Each small change in the timing tells a story of the star's internal dynamics, a brief irregularity revealing a starquake or a sudden transfer of momentum from its frictionless superfluid core. Beyond these precise radio ticks, we also observe the high-energy light blazing from their surfaces. X-ray telescopes study the thermal glow of a neutron star as it pulls material from a companion star, a process that heats its surface to millions of degrees. The specific colors and intensities of this X-ray light allow scientists to map its temperature distribution and estimate the star's overall size, placing a crucial dot on the mass-radius graph. When a magnetar releases a starquake, space-based observatories capture the tremendous flash of gamma rays, giving us a direct measurement of the immense magnetic forces acting on its crust. The most revolutionary new sense in our astronomical toolkit is the ability to feel the universe ripple. Gravitational-wave observatories do not see light, they detect the minute distortions in spacetime itself. The signal from two merging neutron stars is a rich source of information, encoding their masses, spins, and most importantly, their tidal deformability, which reveals the stiffness of their internal matter. This is multi-messenger astronomy in its most powerful form. The gravitational wave signal provides the initial alert, often followed seconds later by a gamma-ray burst, and then for days and weeks by a visible and infrared afterglow as the newly forged heavy elements decay. By combining what we feel with what we see, we build a complete picture of the collision, from the initial in-spiral to the creation of cosmic elements. Each method alone gives us a glimpse, but together they form a composite portrait of the most extreme matter in existence, bringing the heart of a neutron star into ever sharper focus from across the void. To glimpse the heart of a neutron star, we must turn to our own planet's most ambitious experiments. Here on Earth, inside colossal rings like the Large Hadron Collider, scientists recreate a miniature version of that primordial fire. They do not build a star, but they perform a kind of cosmic alchemy in reverse. By bringing heavy atomic nuclei together at nearly the speed of light, they generate a fleeting, intensely hot speck of energy. For a fraction of a second, smaller than the blink of an eye, the protons and neutrons within those nuclei melt away. Their constituent quarks and gluons are set free, creating a droplet of quark-gluon plasma, the very same state of matter that might exist at the center of a neutron star. This tiny, man-made fireball, smaller than an atom, is our closest laboratory analog to the conditions of the early universe and the deep stellar interior. The data from these powerful interactions are not just abstract numbers. They feed directly into the complex equations that astrophysicists use to model neutron star matter. Each measurement of this plasma's properties, its temperature, density, and how it flows, acts as a vital calibration point. It tells our theoretical models whether they are on the right track, whether the predicted behavior of matter under extreme pressure is grounded in observable reality. This creates a profound bridge between the science of the unimaginably small and the unimaginably large. The quest to understand the fundamental particles that make up everything connects directly to the fate of giant stellar remnants light years away. A discovery in a subterranean tunnel in Europe can suddenly illuminate the hidden heart of a cosmic beacon, revealing the unity of the physical world from the quantum scale to the galactic. The true map of a neutron star's heart is still mostly blank space. We have sketched the outer layers with growing confidence, but the central core remains the greatest enigma in nuclear physics. What happens when density crosses a threshold so extreme that our current theories simply lose their footing? Could a solid core form, a crystalline lattice of hyperons or other exotic particles that have never been observed in a stable state? These are not just new ingredients, they are entirely new states of being for matter. The very phase transition into quark matter is a mystery. Is it a sharp boundary, like ice melting into water, or a gradual blurring where neutrons slowly dissolve into their components? Each possibility writes a different ending for the equation of state, predicting a different maximum mass and a different fate for the most massive stars in the cosmos. This vast landscape of unanswered questions is not a failure of science, but its greatest inspiration. It is the very reason we are building more sensitive gravitational wave observatories and launching powerful new X-ray telescopes into space. Every theoretical model is a proposed key, and every new observation is the lock it must fit. The unknown interior of a neutron star is one of the final frontiers for understanding matter itself, a puzzle written in density and gravity that compels us to look deeper. A quiet revolution is brewing in our ability to listen to the cosmos. The next generation of observatories, now in development, will not simply see more stars. They will feel the subtle textures of space-time and hear the faintest heartbeats of distant pulsars with a clarity we can barely imagine today. On the ground, the square-kilometer array will be a forest of radio antennas listening to the sky. Its sensitivity is so profound it is expected to discover tens of thousands of new pulsars, transforming these cosmic lighthouses from rare curiosities into a vast natural network. This pulsar web will act as a galactic scale detector, its rhythmic ticks revealing the passage of gravitational waves so long and slow they are currently invisible to us, and perhaps even mapping the hidden distribution of dark matter. Above our atmosphere, new eyes will open. X-ray observatories like Athena and Lynx are designed to see with a resolution that feels almost like touch. They will not just detect the glow from a neutron star's surface. They will map its temperature variations in exquisite detail, watch how hotspots move as the star rotates, and trace the complex architecture of its magnetosphere. We will see how the star's immense gravity bends the very light it emits, creating a lensing effect that allows us to measure its size and mass simultaneously with unprecedented precision. Each observation will place a new, finely drawn point on our mass radius graph, tightening the constraints on what matter can be, and we will continue to feel the universe shake. The current gravitational wave detectors like LIGO and Virgo are just the beginning. Future, more sensitive instruments, both on Earth and in space, will catch the final spirals of neutron star mergers not as rare, singular events, but as a regular cosmic chorus. With each new signal, we will measure the star's tidal deformability more accurately, directly probing the stiffness or softness of their interiors. This is the shift from inference to direct measurement. We are moving from trying to guess the recipe of a cake by looking at the bakery window to being handed a slice and tasting it. The combined data from these radio, X-ray, and gravitational wave missions will create a unified picture of extreme matter, a portrait so detailed it will almost certainly force us to rewrite our most fundamental textbooks on what stuff is and what it can become under pressure that defies all earthly comparison. These stellar remnants are a tapestry woven from the universe's most fundamental threads. A neutron star is not an isolated curiosity but a cosmic anchor point, a natural laboratory where the domains of the very small and the very massive collide. The bizarre nuclear pasta of its crust, a substance of unimaginable strength, emerges directly from the quantum rules governing atomic nuclei. The frictionless superfluid of its core, spinning with perfect quantum coordination, is a macroscopic display of laws we usually only observe in tiny experiments. And the immense gravity that binds it all together warps the space around it, a dramatic demonstration of Einstein's general relativity in action. Each layer of this incredible object is a chapter in a single, unified story, the story of how matter behaves when every ordinary rule is broken. To comprehend a neutron star is to see how gravity, nuclear forces, and quantum mechanics are not separate ideas but interconnected parts of a single, cosmic reality. They show us that the universe's most extreme environments are not just destructive but profoundly creative. The same immense pressures that can lead to a black hole are also the forges that seed the galaxy with the heavy elements necessary for planets and life. The ghostly neutrinos that carry away a star's final energy are the same particles that help shape its ultimate structure. This synthesis of knowledge brings us to a humbling perspective. We are not just observers of this cosmic drama, we are a part of its legacy. The iron in our blood was forged in a star's final moments long ago. The gold in a piece of jewelry was likely created in the powerful merger of two of these incredible objects. By studying the most extreme matter in existence, we are ultimately learning about our own origins and the fundamental forces that allowed our world and us to come into being. Our journey ends at the frontier where physics itself is being rewritten. We have ventured into a city-sized object where a single teaspoon of material carries the weight of a mountain, and where the very atoms that build our world dissolve into a perfect quantum sea. These stellar remnants are far from silent memorials. They are dynamic engines powering the precise ticks of pulsars, the galaxy-shaking flares of magnetars, and the cosmic forges that create the gold in our jewelry and the uranium in our reactors. To study a neutron star is to ask the most fundamental questions about what matter is and what it can become under pressure that defies all imagination. It is an inquiry into the bedrock of reality. With every new gravitational wave we detect and every faint X-ray pulse we analyze, the map of this extreme territory becomes a little clearer. The interior of a neutron star is one of the universe's final great mysteries, and we are on the verge of understanding it. If this voyage into the heart of the extreme captivated you, we would love to hear your thoughts in the comments. Be sure to subscribe for more explorations into the cosmos's deepest secrets.